Hello everyone, and thank you for attending this presentation. My name is Pat Bhattacharya, and I'd like to welcome you to today's webinar on building smarter models with multimodal data. Joining me today are my colleagues Krishna Mehta, Jisha Augustine, and Ratna Sinha. We will be exploring how combining different data types creates powerful predictive models. So, what exactly is multimodal data? Multimodal data refers to information collected from multiple formats. Traditionally, data scientists have focused primarily on tabular data. This type of data is very structured and can consist of numerical and categorical values. Even today, a significant portion of analytics work revolves around this type of data. And this is just because this type of structured data is easier to process and well supported by existing techniques. However, data is not limited to tables. It also exists in other formats. One such example is textual data, such as product descriptions, customer reviews, social media posts, and other narrative content. Another format in which data is available is image data. Pictures of products, social media images, and real estate photos are some examples of this type of data. Another format of data that is available nowadays is audio and video data. Voice recordings, podcasts, and video clips are some examples. Interestingly, some of these diverse data types have always been available. For instance, product images and descriptions have existed for years. Yet historically, they were often ignored. And this was because tabular data was simpler to analyze and the tools and resources for handling other formats were very limited. Today, however, the landscape has changed. Advanced techniques and computing resources now allow us to process these different data formats. And now we can combine text, images, audio, and structured data. And by doing this, machine learning models gain greater contextual information, resulting in significantly higher accuracy for both classification and regression tasks. Multimodal data are available almost everywhere and can have many different applications. One application can be in marketing campaign analytics. Traditionally, we have only looked at our customers' behavioral data and demographic data. But now we can also analyze the actual campaign images and ad copy. Combining all of that lets us make a much better guess at whether they'll respond and helps us figure out the best people to target. Another example is social media analytics. To truly understand what's happening, we shouldn't just look at the post's impressions and other engagement metrics. We need to also analyze the post's texts, the replies and comments to that text, as well as the pictures and videos that go with it. Looking at all of them together gives us a more complete picture of how well the post is performing and what the audience is feeling about it. In equipment finance, when deciding on a loan, we can go beyond just looking at the company's financial records. We can check out the photos of the equipment to assess its condition. We can look at images of the work site, and we can combine all of that visual data with the usual business data. This makes it much easier to decide on the creditworthiness and the actual value of the asset. Another example is e-commerce sites, which often contain product description, images, and videos. Recommendation engines get way smarter when they aren't just reading product descriptions. They can use the product photos and the videos. And let us not forget the customer reviews, which often include their own texts, photos, and videos. All of this can help to create a super detailed profile That makes the recommendations better and helps with quality checks as well. Another very good application of these techniques is in the healthcare industry. We can have clinical textual data such as patient notes, medical history, and physician reports. Other data for the patient can be in the form of medical images such as X-rays or CT scans or MRIs or ultrasound results, etc. We can of course also have tabular data such as lab results, vital signs, and data from wearable sensors as well. All of these different types of data can be combined to improve diagnostic accuracy and patient outcomes. For this webinar, we developed a multimodal model using home sales data. Real estate provided an ideal testing ground because multimodal data was very readily available. We were easily able to find tabular data on property features, along with text descriptions of the property and high quality images of the property's interior and exterior. This accessibility allowed us to focus on model architecture and modeling techniques rather than data acquisition challenges. This slide contains some additional information on the data that was available to us. We had tabular data on property features such as the year the house was built, the number of bedrooms and bathrooms, square footage of the house, etc. In addition, we had data on the property's location, such as distance to schools and school ratings, flood and fire risk, as well as other neighborhood data. We also had textual data on the property descriptions. These descriptions often included additional notes from the real estate agent, which highlighted some of the important features of the property or location that a particular buyer might find interesting. In addition, we had image data, such as of the front view of the house, and also images of the yard or the porch, kitchen, bathroom, living room, etc. Our prediction goal was time on market, which means that we wanted to determine the likelihood that a single family home will remain on the market for X plus days without selling. And we selected X to be equal to 90, which means we were trying to predict the likelihood that a single family home will remain on the market for 90 plus days without being sold. So our dependent variable is binary. If a home remains in the market for more than 90 days, then dependent variable is equal to 1, else 0. In our data set, we found that about 19.5% of the homes remain in the market for more than 90 days. Note that the 90-day threshold is configurable. 45 or 60 days work equally well depending on market condition and requirements. And why is it useful to predict time on market? Well, if the multimodal model is able to analyze property data, description text, and images to predict the days on market, then this can add value for stakeholders. Sellers and agents can evaluate renovation needs, pricing adjustments, or marketing intensification. For instance, high demand properties can be priced aggressively to maximize returns. Whereas for slower moving homes, they might be able to identify renovation opportunities or adjust their pricing strategy. They can also implement changes to accelerate the sales timeline or maximize property value based on insights. For instance, they may want to optimize listing timing and marketing spend on the listing. To understand how multimodal data impacts model performance compared to using only tabular data, we tested several scenarios. The first scenario is the baseline model, which was built solely on the tabular data available to us. This served as our reference point. In the next scenario, which is shown in the second row of the table, we added textual data. such as property descriptions, alongside the tabular data. If this model outperforms the baseline, it suggests that text provides valuable context and improves predictions. For the third scenario, shown in the third row in the table, we combined image data with tabular data. Again, if performance improves, we can conclude that visual information adds meaningful insights. Finally, in the last scenario, we used everything: tabular data, text, and images. We compared this model's results against the previous three to see whether integrating all data types delivers the best performance. We used many different types of methods to analyze our data. For the tabular data, we were able to use traditional machine learning methods such as logistic regression, XGBoost, random forest, etc. But we did not stop there. We also tried some deep neural network methods and transformer models that have recently worked well for this type of tabular data. We modeled the textual description data using pre-trained language models and the image data using pre-trained vision models. We tried several different pre-trained models and we ended up selecting the ones that gave the best results. I will next hand over the presentation to Jisha, who will talk in more detail about some of the pre-trained models and architectures that we used.
Thanks, Pat. Hi, everyone. I'm Dr. Jisha Agustin, and I will be taking you through the details of some of the models that we selected during the modeling process. For image data, we used a convolutional neural network-based model, ResNet. For text data, a large language model, Llama 2, and for the tabular data, a transformer-based model, FT transformer. ResNet, short for residual network, is a deep convolutional neural network architecture designed for image processing and computer vision tasks. It is introduced by Microsoft Research in 2015. ResNet was designed to make a really deep neural network easier to train. Normally, as network gets deeper, gradient vanish and performance drops. ResNet fixes this by letting layers learn residuals or small corrections rather than the full transformation. Here is the key idea. In very deep network, layers often struggle to learn everything from scratch. ResNet solves this by adding skip connection that skip a few layers. Each residual block learns a small difference or residual instead of the full mapping. Here, f of x is the residual. This skip connection let gradient flow directly to earlier layers during backpropagation, preventing them from vanishing. This allows us to train very deep network effectively. The idea is so powerful that it even inspired modern architectures like transformers. ResNet 50. It's a 50-layer deep residual network. It has a special blocks called bottleneck blocks, which has 1 by 1, 3 by 3, 1 by 1 convolutions with shortcut connections. The bottleneck design reduces parameters and computation, making it efficient. Because of this, ResNet 50 is widely used as a backbone for image classification and feature extraction. Here we can see the ResNet 50 architecture. There are 49 convolutional layers and one fully connected layer. Llama 2. Llama stands for Large Language Model Meta AI, Meta's open-weight family of large language models. The first model, Llama 1, set up the basic transformer structure that powers Meta's language systems. Llama 2 builds directly on that work. It is an auto-regressive transformer, meaning it generates text one token at a time by predicting the next word from the previous one. The same principle behind models like GPT. Llama 2 represents Meta's push toward open, high-quality large language models accessible to both researchers and industry. Architecture of Llama 2. Modern large language models, including Llama 2, are based on the decoder-only transformer architecture. Unlike the original encoder-decoder transformer used for translation tasks, a decoder-only model focuses purely on text generation, predicting the next word one token at a time based on the previous context. Llama 2 introduces several architectural improvements to enhance performance and efficiency. First, it uses pre-normalization, meaning the input to each transformer layer are normalized before processing. It also replaces the standard layer norm with RMS norm, which stabilizes training, especially for larger models. The traditional ReLU activation function is replaced with the swig loop, giving the network more excessive power. Instead of absolute positional embeddings, Llama 2 uses rotary positional embedding or OP, which help the model better understand word position within longer context. In larger models, multi-head attention is replaced with grouped query attention, which improves the efficiency and speeds up inference without much loss in accuracy. Finally, Llama 2 can handle a context length of up to 4096 tokens, allowing it to process and understand much longer sequence of text than before. Let us look at the key components of Llama 2's architecture. Here is the architectural diagram of Llama 2. The Llama 2 model starts with the input embeddings, which combine token embeddings with rotary positional embeddings to give the model a sense of token order in the sequence. Then we have stacked decoder layers, which are the main processing blocks. Multi-head self-attention or grouped query attention in larger models help the model capture relationship between different blocks. Feed-forward network process and transform these representations. Pre-normalization and residual connections improve training stability and ensure information flows smoothly through the layers. Finally, the output projection layer converts the processed representation into scores over the vocabulary, preparing the data for the model's final predictions. Llama 2 7B model. The Llama 2 7B model is the most lightweight version in the Llama 2 family. It contains 7 billion parameters organized into 32 transformer layers, each with 32 attention heads and a hidden size of 4096. The context length of 4096 tokens allows it to process longer passages and maintain coherence across them. It uses a byte pair encoding tokenizer with 32K vocabulary and is trained only on publicly available datasets, aligning with Meta's open source philosophy. FT Transformer, Feature Tokenizer plus Transformer, is a simple adaptation of the transformer architecture for tabular data. Here, each row in a table is treated like a sequence of features. Here is the architectural diagram of FT Transformer. First is the feature tokenizer layer, then the transformer layer. So, the first step is the feature tokenizer, which converts all input features into embeddings the transformer can understand. Numerical features go through a linear embedding layer, while categorical features are mapped using a lookup embedding. This way, every feature, no matter the type, gets a vector representation. Here we can see an example. Here, 3 numerical features and 2 categorical features are present. Before passing these embedding through the transformer encoder, we append a special token called as classification token or CLS token to summarize the row. Then these embeddings pass through the transformer encoder. Like in Llama 2, it uses multi-head self-attention, feed-forward network, and layer normalization with residual connections. Finally, the CLS embedding contains information from all features and a small prediction head, either a linear layer or a multilayer perceptron map it to the final output. Next, we will talk about the result that we see from our experiments. This slide presents the outcomes from our baseline model, which was built using only tabular data. No text or image data was included. For tabular data, there are several well-known modeling techniques such as logistic regression, XGBoost, and random forest. We experimented with many of these approaches and reported the best performing results in the first row of the table shown in the slide. The second row displays results from a deep neural network architecture, specifically the FT transformer model applied to tabular only data. As you can see, both approaches yield result in a similar range, with the FT transformer method performing slightly better than traditional techniques. Next, I will hand it over to Ratna and she will take you through the other scenarios.
Thanks, Disha. Hello everyone, this is Ratna and I will take you through rest of the results. This is case 2 for tabular plus text. Here train AUC is 0.66, valid AUC is 0.67, while test AUC is 0.66. On this slide, we show the results when we include text data along with the tabular data to build the model. The real estate data contain detailed description of the houses in natural language, and we decided to include this information in our models along with the tabular information. To work with the text data, we used Llama 2 model. From the results, we can see that using text data along with the tabular data significantly improved the performance of our model. Now we come over to case 3, which is for tabular plus image. Train AUC here is 0.66, valid AUC is 0.65, while test AUC is 0.66. This slide presents the result of incorporating image data along with the tabular data. The real estate dataset included images of the interior and exterior of the house and property, which we integrated with the structured tabular features. To process image data, we utilized ResNet model. This result clearly demonstrates that combining image and tabular data significantly enhanced the model performance. Now the last is case 4, which is tabular plus text plus image. Here train AUC is 0.69, valid AUC is 0.69, while test AUC is 0.68. In this slide, we show the result when both text and image data is used along with the tabular data to build the model. House description and images of the interior and exterior of the house were used along with the tabular data to build this model. We can see that combining text and image data along with the tabular data significantly improves model performance compared to what we saw in the previous slides. Next, I will hand it over to Pat and she will take you through the overall results.
On this slide, I will compile all the results from the previous slides so that we can look at them closely and compare them. As I mentioned before, to understand how multimodal data impacts model performance compared to using only tabular data, we tested several scenarios. And now it is time to compare them. The first row on this table shows the baseline model, which was built solely on the tabular data available to us. This served as our reference point. In the next scenario, which is shown in the second row of this table, we added textual data, such as property descriptions, alongside the tabular data. From the AUC numbers in the second row and comparing them to the first row, we can see that this second model outperforms the baseline, which suggests that the text descriptions of the property provide valuable context and improve predictions. In the third scenario, shown in the third row of the table, we combine image data with tabular data. If we compare the numbers on this third row with those in the first row, we can see that adding images helps to improve performance. So we can conclude that visual information adds meaningful insights which we may have missed when using only tabular data. Finally, in the last scenario, which is shown in the last row, we used everything: tabular data, text, descriptions, and images. If we compare the numbers in this fourth row against the previous three, we can see that integrating all data types delivers the best performance. Next, I will hand it over to Krishna, and he will talk about some of the next steps.
Thank you, Pat. I want to now talk to you a little bit about what is next for us at Jigyasa. Uh, we have been working with vision models, and we want to extend the work we have been doing to multi-level classification tasks. Let me give you an example. Say you have an equipment and it can be in excellent condition, or it can be in a fair condition, or it can be in a bad condition. What if the vision model could predict that, and assign a score and the likelihood of it being in one of these three buckets, and based on that you optimize and prioritize your work stream and save resources? This is one application, but there are several other applications across different domains where a vision model based classification would be of great use. Uh, then the next thing we are working on is related to synthetic data applications. As you know, we have been doing a lot of work in synthetic data, and you have been getting periodic updates from us and invites to these various webinars. In the coming months, we will be hosting sessions showcasing our applications for reject inferencing, customer churn prediction, fraud detection, and donor acquisition. In fact, in a couple of weeks, we will be hosting the first session where we will be showcasing how synthetic data can be used for reject inferencing. And finally, we have been working with large language models, we have been working with computer vision models, and we have been doing a lot of experiments with synthetic data. And we want to combine all of this for credit risk prediction. And a particular use case which we are very interested in is for the lending of smaller organizations. We have spoken to several of these organizations, and they face challenges related to sparsity of data, data being in non-machine readable formats, or total lack of data. And all these problems have prevented them from doing much more than using their expert judgment to make credit decisions. Now, uh, automation of some of their credit process is a useful first step, but that is not the full scope of what can be done. What we really want to do with them is build credit risk models which help them reduce their risks and get better profitability, and do that using all these applications. So we will be working on that. We have started work on that, and we will be updating you in future webinars about that. Thank you so much for taking the time to attend this webinar today. I hope you found the contents to be useful. We look forward to having you back in a future event. Now, over to questions and answers.